We've already solved linear systems of equations that look like ax equals b. And we've solved systems that look like ax equals 0. But we haven't talked explicitly about how these two things are related, how ax equals b is related to ax equals 0 even when b is different from 0. So let's suppose that we have A, which is an m by n matrix with real entries. Let's look at the possibilities for the solution set of ax equals 0. So first of all, there's always at least one solution because a times 0 is equal to 0. So there is always at least one solution because a times the 0 vector equals the 0 vector. All right, now if rank of A equals n, then this is the only solution. The reason is that the rank of A plus the nullity of A equals the number of columns of A. So if rank of A equals n, then the nullity must be 0. N plus 0 equals n. Nullity means dimension of the null space. So if the dimension of the null space of A equals 0, there's only one zero-dimensional vector space. That's the vector space consisting only of the 0 vector. So the null space consists of only the 0 vector. Now the rank of A can't be greater than n because we can't have we can't have a dimension greater than the number of vectors we have. So n vectors can't span a space of dimension greater than n. So the other possibility is that the rank of A is less than n. So if the rank of A is some number r, which is less than n, then the solution space of ax equals 0, which is the null space of A, has dimension n minus r. So therefore it's infinite. And the reason is that, well, basically the same reason again. Rank of A plus nullity of A equals n. And if the rank of A equals r, then the nullity of A must be n minus r. So we've got an n minus r dimensional space, which is an infinite set of solutions. Now let's look at the possibilities for ax equals b in general, b not necessarily equal to 0. No, there's not always at least one solution. It's possible that there's no solutions. There might be no solution. We would call the system inconsistent if there's no solution. And that's because, so the way this could have no solution is if B is not in the column space of A, then there's no linear combination of the columns, no x, and this x can be looked at as a linear combination of the columns. So there's no linear combination x1 times first column of A plus x2 times second column of A, etc., which is equal to B. What it means for B to be in the column space is that there is some linear combination. But x1 times first column plus x2 times second column that's just A times x. So there's no vector real numbers x such that AX equals B. So that's what happens if B is not in the column space. If B is in the column space of A, and the rank of A equals n, so the rank is the number of columns. Well, the rank is the dimension of the space spanned by the columns. If the rank happens to be equal to the number of columns, then the columns form a basis of the column space. And if B is in the column space, that is, if B is equal to a linear combination of the columns, and the columns form a basis, then that linear combination has to be unique. So the linear combination x1 times first column of A, etc., this has to be unique. Because that's how a basis works. If you can express one vector as a linear combination of basis elements, then that's the only linear combination of the basis elements that gives you the vector you're interested in. So if the rank of A is n, then we have a unique solution. Now another possibility is that the rank is less than n. Let's say if the rank of A is R, which is less than n. Then there's going to be infinitely many solutions. Well, I should have copied down if B is in the column space and the rank is R less than N. So you stick that in there. If B is in the column space of A and the rank of A is R, which is less than N, then there are infinitely many solutions. The reason is if B is in the column space of A, that means that there is a linear combination of the columns equal to B. In other words, there is an X such that AX equals B. Maybe it's worth mentioning that AX is the column space of A. We can think of X as a linear combination of the columns, so I should say the set AX for all X so if we look at all possible linear combinations of columns, that's just exactly what the column space is. All right, so if B is in the column space, then there is some linear combination of the columns equal to B. So we have at least one solution to AX equals B. Now if the rank of A is R, which is less than N, then the dimension of the null space of A equals N minus R. So that means that there are infinitely many solutions, let's say Y, such that AY equals 0. And that means that for each of these, we have a x plus y. So we could add it to x, where x is our linear combination that gives us b. Ax plus y equals ax plus ay, which is ax is b, ay is 0. So that gives us b. So for any of the infinitely many choices of y that solve ay equals 0, we can add that to a solution x satisfying ax equals b to get another vector x plus y satisfying a times x plus y also equals b. All right, let me say that again, and I'm going to mention the basis of the null space a little bit more explicitly than I just did. So let's say we have this matrix, this m by n matrix with real entries. Let's say this matrix has rank equal to r, which is less than n. And let's let u1 through un be one linear combination of the columns of A which equals B. So I'm just saying AU equals B. A lot of mathematicians would say U is one particular solution of AX equals B. Now let's let y1 through yn minus r be a basis of the null space of A. Now, since I can't really do boldface on the whiteboard, I'm using superscripts here to mean this is one vector, y superscript 2 is another vector, y superscript n minus r is another vector. So these are n minus r different vectors which make a basis of the null space of A. So then the set of all solutions to AX equals B is the set of all expressions of the form U plus C1 Y1 plus dot 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 Cn Yn, where C1 through Cn are real numbers, and well, that's all solutions. So we just take one particular solution, any solution we want, and take all possible linear combinations of solutions to AX equals 0. And add those together and we've got the set of all possible solutions to AX equals B. So A times Y, any one of these equals 0. That's what it means for something to be in the null space. Alright, so again, to summarize, this is a lot of words here. If we have one solution to AX equals B, say U, and we have a basis of solutions to AX equals 0, say y1 through yn minus r, then we can take that one particular solution, any linear combination of the basis elements of the null space, and that gives us all possible solutions of AX equals B. So to see this, well, it's certainly easy to see that this is one solution. So for any C1 through Cn, oh, actually, we have n minus r, these vectors, so there should be, coefficients should be C up to Cn minus r, basis elements up to yn minus r. So for any coefficient C1 through Cn minus r, we certainly have A times U plus C1 Y1 dot 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 Cn minus r Yn minus r. equal to, so A times all of this is going to be AU plus C1AY1 dot 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 plus Cn minus R AYN minus R, which is AU equals B, because U is one particular solution of AX equals B, plus C1. Now Y1 through Yn minus R are all in the null space. So that means A times them is 0. So C1 times 0 plus dot 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 Cn minus R times 0. So we've got B plus a bunch of zeros, which is just B. Okay, so that means that any vector of this form is certainly a solution of Ax equals B. Any solution you want, plus any solution of the homogeneous system Ax equals 0. Anything in the null space, that is. So now let's look at why these are the only solutions. So to see that these are the only solutions, let's suppose W is another solution. So if W is another solution, then we have that A times U minus W, or let's say W minus U, equals AW minus AU, which is B minus B, which is 0. So that means that W minus U belongs to the null space. But then, since we have a basis of the null space, these y1 through yn minus r, since y1 through yn minus r is a basis of the null space, so then any element in the null space, I guess, is a linear combination of those. So we have W minus U equals something like D1 Y1 plus dot 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 D n minus R Y n minus R for some D1 through Dn minus R, which are real numbers. But then W has the form W equals W minus U plus U, which is a sum of DIYI, that's the W minus U part, and then plus U. So W equals particular solution plus some linear combination of the basis of the null space. And this was already included I've erased the theorem. So this was already included in our stated set, our stated solution set, which was U plus C1 Y1 dot 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 C n minus R y n minus R, where these coefficients are all real. So if we find another solution W, it's really part of the solutions that we already listed. So it's true to say that all solutions have this form. All right, now let's do an example, which is really nothing new, but I just want to look at the example in terms of what we just said, relating the system of equations AX equals B to the related system AX equals 0, to see how the null space works its way into the solutions of AX equals B. So for example, let's find all solutions of 1, 2, 1, negative 1, 1, 1, 0, 1, 2, 3, 1, 0, x1, x2, x3, x4 equals negative 1, 2, 1. So we'll just use the same exact procedure we used before. We'll use row operations. So performing row operations on the augmented matrix 1, 2, 1, negative 1, negative 1, 1, 1, 0, 1, 2, 2, 3, 1, 0, 1. We have, let's see, so row 2 is going to be row 2 minus row 1. Row 3 is going to be row 3 minus 2 times row 1. And we get 1, 2, 1, negative 1, negative 1. 1 minus 1 is 0. 1 minus 2 is negative 1. 0 minus 1 is negative 1. 1 minus negative 1 is 2. 2 minus negative 1 is 3. And row 3 minus 2 times row 1. 2 minus 2 is 0. 3 minus 2 twos is 3 minus 4, which is negative 1. 1 minus 2 ones is 1 minus 2, which is negative 1. 0 minus 2 negative ones is 0 plus 2, which is positive 2. And then 1 minus 2 negative ones is 1 plus 2, which is 3. All right, so we can immediately cross off the third row because we see that that's just equal to the second row. It doesn't give us any more information. And let's multiply the second row by negative 1 just for convenience. And we've got 1, 2, 1, negative 1, negative 1, and 0, 1, 1, negative 2, negative 3. So our solutions have the form, we've got two free variables. X3 and X4. So we can say X4 equals T, X3 equals S. And then this equation tells us that X2 plus S minus 2T equals negative 3. In other words, x2 equals negative 3 minus s plus 2t. And then the first equation tells us that x1 plus 2x2 plus s minus t equals negative 1. Or in other words, x1 equals -1 minus 2x2 minus 2 -3 minus s plus 2t minus s plus t.